All right. Well, I guess group is large enough, so let's start. Um, MX3D 3D printing already for around 12 years now, and since 11 years we are an official company, and we focus fully on robotic 3D metal printing using welding robots. And our innovation, so to say, is to add software sensors to that mix so that everything goes more and more automated. So the theory of printing or welding layer on layer and creating 3D geometries like that is of course already really old. But the development since 2013-14 with both robotics, software and sensors have gone so fast that this idea now finally becomes something that you can use in your manufacturing use cases. So some generic reasons to use additive manufacturing are to reduce your lead time. I think this is probably one of the most prominent ones that we find people coming to us to see if they can have a machine operational that basically can replace casting and forging, and so have some parts available again within hours, weeks, instead of months or years. Um, so another reason is to reduce the stock that you need because you can reduce your lead time, because you can digitize everything, have your part ready digitally in a database. You don't need to have that big stock anymore. You can reduce it to the absolute minimum. So of course you still need one part to replace right now, but then anything after that you can then print on demand. So we really see not only quick replacement as one of the functions of 3D printing, but also to reduce the stock, and this could have a very significant effect for the stocks of big oil and gas companies. So we also make your supply chain more robust, more flexible. So if your OMEs understand that there could be a print in your own facility done, and you're just coming to them because they have more experience, they have more machines, then they experience some price pressure, some lead time pressure. So you're actually making it clear to your entire supply chain that it's needed for them as well to boost their game and come up with quicker lead times and lower cost. And otherwise, you can just make it yourself. Um, So just a little bit about MX3D. So we got became a real company in 2014. We now have a 15 robot workshop. The biggest robot has multiple robots and can print parts up to 20 tons. But most of the robots, they can handle parts up to 2,600 kilos with 8 axes. So that means, as you see here in the photo, that you can turn your workpiece so that you can really approach the workpiece from every side and print it in the most ideal fashion. So we now have around 40 people working for us. Many of them are welding engineers, robotic engineers, software engineers, and of course, we have a quality team and a general team, amongst whom is myself. So I don't have a technical background myself. I hope you can forgive me for that, but since 12 years, I picked up something here and there. Um, what we do as a business is we print parts on demand for customers, and when they're ready to take this technology in-house, we can deliver the systems. So we have a basic system, but we also have an extended system that can be basically made up to spec. So WAAM, for who doesn't know, WAAM is 3D printing with a welding robot. So we use off-the-shelf equipment, welding robots that have been used for the automotive industry already for a long time. Same for the welding power sources, and most of the sensors are coming from welding. So all we do is create a system that you can scale up really easily. So both in size. So as I mentioned, we already have a machine that can print parts up to 20 tons, but also in volume. So if you have a part and it works out, and you need to print not just one, but maybe 20 every year, and therefore you need more machines, we can have new machines on your doorstep in 2, 3 months' time. And this is one of the attractive parts of this technology. It's really a technology that already belongs to the regular workflow of your company. Probably already have a few welding engineers walking around that can now, instead of judging the quality of a regular weld, can be transferred to the new 3D printing scene as well, where the same logic and know-how applies as in regular welding, also to qualify the parts. This is an important source of information. So we we always have quite a long list of materials that we already work with. So some of the materials we really have tested together with DNV, Bureau Veritas, or others. And others we just have quite an extensive experience in printing larger parts for. But in general, you can say that most of the welding wires that allow for stacking welds on top of each other with good quality also allow for 3D printing in the way we do. And this is really a big benefit compared to other 3D printing technologies where maybe you work with powder and there's only a few types of powder available for a certain alloy. In wire, there is already a lot more availability there, and the cost for wire is considerably lower than for powder. So again, just like with the machine where the capex are relatively low, also on the OPEX side, everything is just standard welding material, welding gases, welding consumables. So the cost for your material in that sense is as low as it can be. So, I mean, for welding wire, for those who aren't accustomed to that, I mean, if you just want a regular steel wire, it can cost as little as €1.80 per kilo, and stainless steel maybe 5 or 6. So if you're used to powder bed, for instance, these are prices that are quite new. And one of the big advantages of this technology as well is that you not only have a relatively low material cost, but you can print it at a much higher volume than most of the 3D printing technologies out there. So you have to imagine that a normal 3D printing deposit rate in our terms is around 2, 3 kilos per hour. We can sometimes go up to 5 or 6 if it's a part that allows for this, and only if it's really refined printing we would go down to 1.5, 2. But yeah, if you know that for most powder bed printing, for instance, you're talking more in hundreds of grams per hour than in kilos, this is a huge jump in terms of efficiency and scale in general. Well, one of the questions that people typically ask, especially in the high demanding industry, is that, yeah, what about the quality? Can you match the casted part quality? And what we always like to show is an image. It's going around already for a while now, but this really shows for me the level of quality we can achieve with WAAM. This was with nickel aluminum bronze, quite a complex material to print, to weld, but still with this material we managed to get a level of inclusions that are radically lower than the casted part that we were replacing with this. So not all materials have exactly the same qualities at the end of the printing. That would be too easy, but for several materials already we have reached forging quality, and for quite a few others we reach near forged quality after printing. So yeah, maybe aluminum is a bit more difficult, nickel aluminum bronze is a bit more complicated to manage, but in general quite a few of the steel, stainless steel, duplex, Inconel variants are very well, yeah, can reach a very good end quality. So prints are made near net shape. So this really means that what we make is sort of a near perfect forging block. So it's almost the geometry that you need, but you still need to mill off 2 to 3 millimeters on each side where you need absolute precision. So yeah, this needs to fit in your budget. If you can cast parts and after casting they're immediately ready to go into the feature that they're used for, then maybe it's a hard fit. But if your casted part or your forged block needs extensive milling as well, then yeah, the process of WAAM is probably a good fit for you to look into as well. So we have minimal material losses, especially for materials where the wire cost is relatively high, like Inconel. This can turn out into a very good cost saving factor alone. And then also imagine that if you have a material that is not as easy to get in a block, so maybe an Inconel duplex of 1 by 1 by 1 meter, that's not a block that people just have lying around. So with printing it, you only have to buy the wire, which can be on our doorstep within a matter of days. You can actually start printing, and if you print 4 or 5 kilos per hour, you can already quickly get an idea on how fast we can deliver a 500 or 1,000 kilo part. So this is typically quite a lot faster than having the block forged or casted and then brought to your milling capabilities. Yeah, so guidelines are developing, so it's definitely not that every industry and every use case already has a fully functional WAAM standard available, but it is growing rapidly since a few years. So we already have a few generic ones like API 20S and DNV BT203 that allow for certain industries to have parts printed with WAAM or DED, directed energy deposit. We also do have printed some parts for the European Pressure Directive, the PED, ESME Section 9. And this, to me, already shows that there is a lot of opportunity for WAAM to be included in the broader industry as well. So we already know of quite a few commissions where DED WAAM is now in the last phases of acceptance. So we're expecting quite a few more of these to come out, and as soon as it is a standard, you see that the number of orders for actual production parts grow in that sector quite a lot. So this is something we expect to grow with a number of standards every year from this time onwards. So yeah, a nice example is nuclear. We expect some standards coming out there, allowing for this technology to be used in some criticality levels as well. So I mean, for some standards, it's just the standard that actually blocks the use. So where they say this part has to be made by use of casting, then of course it's very hard to replace that with another technology. So they need to open up. Some standards are already a bit more open, and you can, after discussing with the certifying body, you can sometimes already use WAAM because it is a type of welding, and if it allows welding to approve for your part manufacturing, then this could also be a solution. So what we do is a lot of emergency small series parts. So if you only need 2 or 3 highly specialty parts and specialty materials, then it makes a lot more sense to, instead of setting up a whole supply chain with quality control across the ocean, to have a machine that can make that much closer to home. It's faster, quality control remains yours, and also the fact that you can keep IP very close to your core organization. That is another benefit of not having to need an entire supply chain as well. So replacing these parts requires first time right, and this is something that our company has been working on. So compared with other 3D printing technologies, WAAM has one big advantage, and that is that it is just welding. You're stacking welding layers on top of each other, and if something might go wrong at some point, it doesn't mean that the whole part is lost. Obviously, that's not what you want. So what we have been including since a few years more and more is a number of sensors that allow you to follow the print during the build-up, so that when anything seems to be going off, then either the robot, the system is intervening itself as far as it's allowed by the standard, or it stops and asks for one of the welding printing engineers to make a small intervention or to make a decision. So here you see what we do. So we have a software that builds up the whole part from scratch, and everything is done automated. So you only have to select which features you want to print when, and then from that point on, the whole toolpath planning and the control is all automated. We also do quality control at the end, so we have a full log of all the data that you need. But we can also scan the part for geometrical control and then send it out to the milling company, so that allows the milling company also to have a good reference point, which is sometimes quite complex if you get a part like this in. So that speeds up the process there as well to make it all fully digital. So yeah, great example that we have been doing a few times now already, and I think some people on the call have experienced this as well, is like these emergency clamps. So when you have a chemical or energy factory, sometimes you identify a potential risk in one of the pipes, and you want to make a quick and dirty repair. It doesn't have to be perfect, it just has to hold until the next shutdown of the factory 1 or 2 years later. So you make a quick repair, and yeah, this turns out to be a very efficient way, especially again when you have to make it in duplex or some kind of a specialty material that is hard to mill. You can print. And here you see a nice example where we didn't just come up with some kind of an intervention print, but also we printed on existing parts. So we reduced the amount of kilos that needed to be printed, and we could make the fit for the clamp much easier as well. So this is called hybrid printing, and for that it's also really handy to have the 3D scanner on hand. So here again, you know, we build a DPS, we call it, so a deposit parameter set. This allows you to show the welding inspector or a DNV, Veritas, that everything was built up in exactly the same fashion. Sometimes you need multiple DPSs to build one part, and then you need a few certificates like this. So basically see it as a material certificate, but then for the printing strategy. We, of course, for a lot of materials, we have built out this knowledge already, so this makes it a lot easier to get started. And soon we will also have a DNV additive manufacturing facility qualification, so this will again allow us to kickstart projects much faster and with less intervention from these certification bodies, because that, of course, is in a way almost paradoxical to what you try to achieve with these kind of quick intervention builds. If then the certification process takes still relatively long, then yeah, it's a shame, because the production and the final delivery of the part still takes long. But we're doing everything we can to reduce that, and therefore have yeah, a highly qualified quality already out in a shorter time frame. And yeah, this is also something we need to build out with our customers. So the more and more experience in certain standards we have, the quicker it goes, and this is something that's an ongoing process. So we have reverse engineering possibilities. So we have a 3D scanner. We use the 3D scanner to intervene during the process. So every 20 layers or whatever you set it to, you can do a quick check to see whether the buildup and the geometry of the part are still going okay. So that's one of the hardest parts to see with all the welding information. You don't get a fully how do you call that, geometrical site of your part. And that's what we use the 3D scanner for, and then we can make an automated quick repair if needed. But another aspect of this is that you can scan a part that you already have and you want to print some features on it, or you have a broken part and you want to repair it. Then this allows you to yeah, make the first scan of the original part and then fill in the rest. So I have a small video for that as well. I will cut the sound is already out. So here you can see, I mean, the tip of this tool was broken, so we cut it off neatly, and then we scanned it, we filled it in with the automated toolpath generation, and then it's a matter of, I don't know exactly how long this took, but this probably a half a day or something like this, and you can have it repaired and milled if you need. The same tool we can use also for cladding. So obviously what we use is just also used as a cladding machine, and with this scanning tool you can use this as well. So this allows you to have a 3D printing robot in-house, and at the same time make sure that yeah, you can add processes like cladding or printing small features on top in one machine. So as I mentioned, it's a very scalable production machine. So we have already a few customers that are printing volume with this. A BMW Group, I think, is the nicest example. They have multiple machines, and they know how to use the machine to print a small series. What for them is small series, but for most of us here on the call, we would consider that quite a large series. So once you've printed parts a few times, the follow-up parts are getting easier because all the settings are already there and the control system is completely teached into a specific part. So if this makes a lot of sense for you, so we have a company, for instance, that print flanges, and the flanges are always a bit different and sometimes of a different material, and they never know which one they need next. And a machine like this really allows them to just have the part within a day whenever they get the need of it, and they can significantly reduce the stock that they need for this specific item. And yeah, for BMW Group, that's the same. So you know, they make these small series of specialty cars, and they need to make some small adjustments to basic parts that they already have. So reinforcements or small additions per separate car, and for them that's a small series, and with this machine they can repeat that over and over again. So I think a few of the projects show you where this technology is already, and some people don't always realize yeah, how quick it's going. So I think only 4 or 5 years ago the industry really started taking notice of wire arc additive manufacturing as a technology that was going faster into industrialization process than many of the other additive manufacturing technologies. But by now you see that quite a few organizations are incorporating it. So you have US Army, US Navy, but also Framatome, which is a big nuclear company in France that is building a whole factory around a few of our systems. And this shows that they did this after 4 years of project together with us, and to me this really shows that you know the quality that you can achieve is already convincing people in the nuclear industry that it has a certain consistency and level that allows them to make these kind of investments. This is one outcome of the collaboration that we had with Framatome, but another outcome is that EDF, the mother company of Framatome, the big nuclear company in France, is now a shareholder of MX3D. So yeah, we definitely also see a clear future in the nuclear industry because there it's all about quality, consistency, and sometimes long breaks between two big jobs. So this technology where you can make a job and then you don't lose any of your knowledge because everything is stored digitally. So by the time you need it again 3 or 4 years ago, it doesn't really matter whether the person that made it a few years ago is still there. You keep the knowledge inside your company with the machine there. You always are ready to go again when the opportunity arises. And the availability of manufacturing capacity is something that is one of the biggest concerns in the nuclear companies, because after a long break, now the nuclear is popular again, but now much of the manufacturing capabilities are missing again. So they're building this up, and we really see a lot of interest from companies to move into this technology as well. Um, so for Total Energies, so we're part of the Field Node. Field Node is a organization that brings together quite a few of the big players, so Shell, Exxon, Total Energies, Equinor, and several others. And they have set up a platform for additive manufacturing, where the buyers basically can reach out to multiple suppliers, and they want to facilitate the knowledge that everybody has around building up these parts with this new technology, so that not every company has to learn it again, and so that suppliers can also use the knowledge from previous projects. And so one of the projects with Total Energies we did is a part that goes on a turbine which is under pressure, and we were able to follow all the standards that were relevant for this, and therefore creating a legacy part that there was only some drawings from a part from the 60s. We could produce that, test it, and then place it back on the machine, and that all relatively quickly. And as you can see, it's not that big of a part, but it is rather complex, and yeah, we made sure that there was no need to build a fully new replica to have it casted, but we could have it printed locally. Um, just a little bit about our software and machine. So as I mentioned, we print on demand because we believe that when you're interested, it might be best to first try out a few parts to convince everybody around you that the quality and the precision is good enough for the applications that you have. But then when you're ready, then yeah, we are ready to supply also systems to either you or to an OEM of your choice. Um, so what we have built is really, the customer brings the cut file. It's your design, but from there on, every step is included and automized, and it's all built up in-house. So you don't need multiple software packages stitched together with an imperfect fit, but the flow is fully made internally. And there is other people that have good slicing software, but one of the things that we see now is becoming more and more important for companies that operate in an energy environment is that it also has to be done according to the standard. So you have to, at the end, be able to prove that you can log everything in the right way. Even also, if you have multiple DPS is used in your part, you need to be able to show that everything went in order, and that the machine was approved, that the operator was approved, and that there is no misalignment with the standards out there. So this is something that we really work on. That is something that you don't obviously see from a software, but it is a very important part. And I think, yeah, if you can take in that we are actually delivering qualified parts. We are the first printing facility that experiences the pain when a software is not operating as we need, and so therefore the development loop within MX3D is very short because the software team is also here, and yeah, if they make a product that is not yet up to spec with what the manufacturing department requires, then the discussion about that is very rapidly evolving. And so therefore, I think we've built a software that's really resilient and functional. So it has three basic steps. So you have Metal Cam, Metal Live, Metal Viz. So Metal Cam is basically, allowing you to print the part in various ways. We we can propose, the software can propose the way it would do it, but you can also direct it a bit more if you have a specific idea of how you want to build it up, in which segments you want to do first or all alternating. This is something that you can assign. Then you have Metal Excel Live, which basically follows the print. It tracks 60 to 70 parameters during the print. And if any of these parameters are crossing a certain benchmark that you can set, so a top and a bottom benchmark, then there will be an action. Either the robot can intervene with a predefined and admissible action, or it gets an operator in there. But this really makes sure that, even if there is something that is not going according to the original plan, then at least the robot is not just continuing the print for you to find out 2 hours later that it wasn't going well. So this allows us to print much more first time right without any interventions like grinding or something, which if you ever had to do grinding on a part like this, that is one of the things that you really want to prevent. So this is what Live is for. So it also logs when you open the door, when the gas flow is interrupted or something like this. So you really have a very detailed level of information about your print. So it also allows you to research. So if it's not for production yet, or you want to improve the productivity, you can really dive into all the data and see where the robot is still waiting long, or the interpass temperature makes it a bit slow. Then you can decide how to maybe solve that in the next sprint. And then Viz is basically all the data logged for you, so you can visualize it to see quickly what was going on where. But of course, all that data is also available in all formats that are usually used for this, and you can export that for other analysis tools. So we basically have 3 systems since a short time. So a simple system without all the guarding. If you have already a fully functional welding setup, you can just put your welding robot next to the others in a way and start printing with that. We have a turnkey solution, that is the small one here on the image, which can print parts up to 750 kilos and roughly 1.5 by 1.5 by 1.5 cubic meter. But if you want to go much bigger, or if you have something in mind that requires a different type of axis, or the robot higher, or 2 robots printing at the same time, then we can design that system for you, with you. And so we have now systems with multiple robots to increase the deposit rate, especially for when you have a big, relatively simple part which would benefit a lot from extra kilos per hour. This is something that's in there. And yeah, because we built the software from scratch, we have this already on the plank, we say in the Netherlands, but we have this ready to go, and we can adapt really easily to new kinds of configurations. And that's also why we chose the robotic platform compared to a say 5-axis CNC kind of platform, where once you want to scale that up or change something in that, it's much more difficult. But the robotic platform is much easier to do that for. And what we always say as well is that the precision that a CNC kind of setup could offer you is actually already higher than what you would need for a WAAM setup. Because as you see, when we print something, then you have a welding skin that is maybe already 1.5 millimeter deviation from the final part that you want to achieve. So to have a machine that can have a 0.1 millimeter precision is in that sense not that relevant for this technology. And therefore we choose the robotic platform. It's much more flexible, much more available, much more scalable than the other ways of doing this. So I will flip through this a bit quicker. I mean, I think the what is the most important to know is that we don't bring in some kind of a fixed alloy library that you have to use, and you have to use our wire to get good results. It is fully built with the understanding that you will probably need some different alloys in the future, or you're going to have a different supplier. So you can make your whole material file as large, complex as you like it, as many DPSs as you like per print, and we make that as easy as possible, because this is something we experience we have to do quite on a regular basis. So this is fully open system, and allows you to do your own development on new materials as well. So yeah, the tracking, I think, is really important, also for understanding what went wrong. So we're now introducing also an AI tool that tracks all the parameters live, and sees what causes what kind of imperfections or events that would block or delay the printing. And yeah, more and more we will see the results of having a more tailored response to these kind of events. So we are always careful saying that we do on the fly repair. I mean, with all the standards, you don't want to do too many repairs. I mean, maybe if it's not running very stable, you should first go back to the drawing board and make a very good deposit strategy, the parameter set. But it does give us more and more insight and on what is probable causes for certain aspects of the print not going perfect. And yeah, this will make the automation of the system higher and higher as the years will go on. Yeah, so I already explained you a bit about Viz. Here you can also see really the level of detail. So for every one of these points, you can literally figure out what the parameters are for that. So we have the 60 or 70 parameters. So you can really go deep into each problem that occurred. So that's it for my presentation. I hope I can leave a bit of time for some questions. So I have Andrea next to me, who is probably going to give me some of the questions as well. Any questions from the audience that came up? We have a few already in. So Harry says, for parts which are using parameters which have not been qualified for pressure equipment, what's the rough timeline to go from concept to fully qualified part production? Yeah, so the timeline for that I think is at least a few weeks, right? So what we basically have to do is we have to print a few parameter sets, send them out for testing, and with that DPS we can then print. So I would say that most positive there, you would typically have 3 weeks before you get the DPS is fully tested. Could be a bit faster. So yeah, what the process will definitely would look like is that we would book in with you and our international welding engineer, the quality manager. We would book in a meeting where we identify what standard applies, which material you want to use, what are the benchmark values that you need, and what the standards prescribed. And based on that, our engineer then makes uh, the parameter set, and that parameter set is then being tested. I think this is something where we're working on as well a lot for making this easier over time. So that's why we have this DNV um, facility facility certification coming up. So this really allows us to print more materials ahead of time without the need for supervision by someone from DNV in that sense. So we can basically pre-qualify more and more materials for also these kind of pressure equipment tests, and yeah, so this will allow us to shorten that time even more. Um, Yeah, I think for pressure containing parts, we have now done a few. So if you have specific questions, as I mentioned at the beginning, I'm not the welding engineer, and I'm always terrified of saying something that sounds stupid on this respect. But our engineers can run you through how we qualify those parts, and as we've done it now a few times, this should be something they can quickly tell you. But in large respect, we can already follow the PED in this aspect, but hopefully, yeah, with the facility qualification, we can run through that process a bit quicker. Yeah, so what we use as a process is basically MIG welding machines, and of course, the cold metal transfer, the CMT of Fronius. There is some other cold metal transfer machines out there now, but yeah, our machines are mostly the Fronius one. Yeah. So the qualification SME Section 9 is mainly for these pressure-containing parts, and these plus the PD they have now WAAM and DDT really included, so that allows us to make those parts according to a full quality package, and then have a good result. So you do have to do the pressure testing typically at the end, at least in the projects that we've done so far. So there is some actual testing involved of that at the moment. So I don't know if. All right. So which parts of the value chain must be in-house versus partner-based machining, heat treatment, NDT? Yeah, it's a very good question. So we do only 3D printing in-house. This is what we specialize on. We are also, because we are a mixed company, we don't only focus uh, on printing on demand, but we also develop the software and deliver the systems. So at the moment, we don't have machining in-house. We do have partners for machining, heat treatment, and NDT close by, and they're very used to working with WAAM. So I guess this is for everybody to decide for themselves. So ultimately, of course, customers, they don't care whether something is wound, printed, casted, or forged. They just want a solution for their problem. And machining, heat treatment, NDT are part of that to reach that. So yeah, if delivering really quickly is one of your key features, then I would say that it makes sense to have everything in-house as well. So yeah, here's a question also about heat treatment. So yes, we typically do heat treatment after the parts are printed. So this depends a bit on the standard that you apply, which one. So typically already when we set the DPS, we already define the heat treatment, and we do the tests also including the heat treatment on the blocks, so that you get a good view of the end result. Other post-treatment are typically milling as well. But we've done everything from sandblasting to painting to electrolytic plating. So anything basically that you can do and have to do with normal metal parts, you can also do with these parts. So here's a question about the LRQA certification. Yeah, so the LRQA, it's a certification that used the guidance notes by TWI and Lloyd's Register Foundation. So these were one of the first ones that were developed for WAAM DED, and that's why we were also one of the first ones to get these LRQA facility qualification. So they have been evolved, but there is now quite a few extra ones out there as well, and I think the DNV one is at least 1, 2, or 3. So yeah, it depends a bit, I guess, on which sector you are operating in. You have the most ambition to grow, to see which one is the one that is most suitable for you. So we get a question on how much training would it take to use a machine, and whether we offer the training. So yes, we offer training. So when we put a machine down, people get the nuts and bolts after, within a few days. This allows them to print small parts, simple geometries, and typically after 2 or 3 months of playing around with the machine or printing some parts, we come back for a more extensive training that really goes into all the questions that you get once you actually start using the machine. So that's what we always offer with all the machines. What we say is that if you hand us someone that is already accustomed to operating a milling machine and preferably has welding knowledge, then yeah, they will be able to understand how this machine works and operate it. I mean, we made the robotics part and the tool part rather easy, but identifying how to make a successful print is in large respect still dependent on the welding process. So if you're using a new alloy and you have someone that doesn't know anything about welding, then it's quite hard for us to, yeah, automate that in a way. So that's typically what we say. Try to have welders behind the machine, and then, yeah, as I mentioned, within a few days they can print the first parts, and then, yeah, I guess it just takes a bit of time to get to understand all the options that the machine has to offer. I mean, our software is pretty simple because we only focus on WAAM, right? We don't do anything else. So all the buttons and all the sliders that are there, or all the options, are just for this process. So yeah, we believe that this facilitates working with it. But yeah, like any machine, you need a few running hours on that. Yeah, so what is the best robot for 3D printing? I mean, I think if I have to say it from our perspective, I mean, we use ABB and KUKA. They're both perfectly fine. We don't have a huge preference in that sense, and we also don't think that yeah, many of the industrial robots, they operate in a similar way. So we don't, in that sense, think the brand of robot is super important. It's more the brand of power source, because this is a power source game. And also there's a few good options, but yeah, once you get one and you build up a lot of knowledge around one power source, then it's harder to replace that with another. Yeah, the build up rate in kilos per hour of this process is in general somewhere between 2 and 5, maybe 6 kilos per hour. We can technically go faster, so it's not a problem to print 8 kilos per hour. But so far in qualified projects where we have to meet certain benchmarks and certain how do you call it, quality levels, then yeah, 6 kilos typically on the higher end. And what you see as well is that you need a relatively bulky print for that. So if you have a very thin wall and it's only like 20 centimeters long, then your deposit rate will be much lower than when you have a very fat, thick block that you can print, and that the heat dissipation is a lot better. So yeah, for bigger, fatter, 500 plus kilo prints, you can reach a much higher build-up rate than for thinner walled, smaller projects. So a few other questions that come in. Yeah, so the thermal management we use is so the very basic is just having the pyrometer measuring the temperature before you start welding again. You need to know whether you meet the bottom and the upper interpass temperature. We build up parts in that way. So as there is not really a lot of modeling out there yet that can predict how a part will behave if you build it up due to the thermal yeah, stresses that are building up. We don't have those in our software. Many universities are working on that, but as far as I'm aware, there's no one that really cracked the code yet to make that as efficient as it should be. So it still takes many hours to have one line calculated. So if you print something with 100,000 lines, then this can take a lot of time. So is it possible to take an existing, couple it with a Fronius and two-pot planning? Uh, yeah, I mean, we used to do that. We started out with someone had an ABB already, and we fitted it out with a welding machine and our software. There's a few things that are not ideal. There is that we do have quite a few requirements for the robot in terms of software, etc. And what we've seen sometimes is that just adding 4 or 5 blocks within the robot controller can cost like 10, 15K. It takes a bit of time to figure that out, and so it can be a bit more frustrating to use already used equipment, but in theory it's possible if it's exactly the same as what we need. But yeah, upgrading robots, that's the earnings model of robotics companies. So what we've seen typically is that people often choose for buying a newer one once they've seen it. Um, so I see someone, yeah, a question on whether we have machines in the US. Yes, we have. So there's already a few machines there. The US Army is a nice example of one that you cannot visit, obvious reasons, but very soon we will have a one on the East Coast that is actually meant for demos. So definitely reach out to me and I can connect you to the people that will operate that machine. So here one more question about the maturity. So is there still something crucial missing for WAAM to be introduced, or is it only about OEM's capability to adopt this technology? Yeah, so I mean, the very biggest puzzle piece was the standards that weren't there, and they are now coming in. So first things first is, are the standards for the specific industry that you're servicing there? If yes, then there is in principle not a blockade anymore. There will always be a blockade from people that haven't worked with the technology yet and they need to be convinced. But we see that once there is a standard and you have a welding engineer or quality manager on both sides, yeah, I mean there's not really a question anymore whether this could work, but the question is just, can we make this work in a commercial way? And I think if there is any blockade when there is a standard available, then it's probably more a commercial one than a technical one. So yeah, I mean on the commercial level, that's with additive manufacturing always exciting because you need typically, you need to add a few benefits of this type of manufacturing together to really get the broader picture in that sense. So I mean, yeah, how much is it worth to you that you can have a part 5 months earlier? I mean, of course, if you're in an urgent situation, you need to replace right now. It's really easy, but maybe some company wants to replace their casting and forging, but they don't have this urgency for this immediate part yet. So yeah, sometimes you also need to help the customer in that sense to figure out where the value for them is. And yeah, the more open the relationship is, the better we can explain what the value of the WAAM parts are. And yeah, sometimes this really solves a problem, and sometimes casting or forging is still the better option, and that's I guess a discovery. But what we do see now is that people start already to engineer and design their parts with WAAM in mind. So more students come out with familiarity to this process, or customers that are already working with WAAM now for 5, 6 years. They now just when they go design a part that's suitable for WAAM, they already take it into account and they immediately make a part that works well for us. Um, so yeah, I think on the monitoring and welding, so on the in situ monitoring. So we don't use anything besides our Metal Excel suite to check the whole process. So I think that's also one of the benefits. It is possible to hook on a new sensor that we don't have yet. So we have a thermal camera, we have a well pool camera, um, yeah, the 3D scanner, the acoustic sensor, and a variety others. So if you want to add something else, that's possible, and then every data that is brought in by that sensor is going to be timestamped so that it's exactly in line with all the other data. So even though we are now using only Metal Excel and the sensors connected to it to check the print. If you have another sensor that is really relevant to your industry, then we can add it and make sure that the data is really streamlined with the rest of it. Um, with that question, I want to close up because we're nearing the end of the time. I hope this was insightful for everyone. If you have any follow-up questions, feel free to reach out. We're always happy to partner with you to print an initial part with you, or to go with some exploration mission to figure out whether WAAM works for a specific case. This is what we're here for. So thanks everybody for your attention, and hopefully see you soon.